Sir, please start the recording.
Yes.
Okay.
I'll start. Also, you can start. If I forget the CR, already recording is started. Okay. Recording is started by someone. Yes, if I forget in any way, the CR, you will start the recording. Acha. If we see here, the current means the net flow of charge, rate of flow of the carriers, charges. So if we consider along this direction, the electron can move randomly along any direction, say like this, along this direction, this direction, this direction. And this type of movement is known as random movement. Now, if you consider the random movement of some such electrons, and if you want to get the net flow of electron along a particular direction, so what would be the resultant flow of charge carriers along a particular direction? Can you tell anyone? Along a particular direction, say this direction. What would be the net flow of flow of the charge carriers here, the electron? Response, please. Can you see my annotation here? What I have drawn here?
Yes, sir.
Okay.
Yes, sir.
So then, what would be the resultant uh, current flow along this direction? This is nothing but the vector sum, resultant vector sum along this direction. And what would be the resultant vector sum along this direction? Just if you consider this component, so it has one component along this as well as this component, and similarly it also has one component and along this. Also this has, look at this, these are randomly moving in all directions. So as a result, each component will have some equal and opposite component in the other direction. As a result, the net flow of the carriers along a particular direction, that would be zero. So that's why for Brownian motion of the random movement, you will not get any net or resultant flow of carriers along a particular direction which can give the resultant current. That's a zero current. You will not, it will not give the any current along a particular direction. So now if you apply a field, that is what force, then this Brownian motion of the electrons is actually drifted or derived to force along a particular direction. That is what is known as the drift velocity of the electron, in which that electric field, actually that force, drive the electron to flow along the particular direction in opposition of this Brownian motion. So if you apply more electric field, more number of electrons will drive towards a particular direction, that is the direction of the electric field. And that's why you are getting the current, right? So and now if you increase the temperature, more electron will move, the Brownian motion will increase. That is the random velocity, that will increase. And you will need more force to drive the electrons along a particular direction. That's why you have to, that resistivity actually is increased. This Brownian motion actually increase the resistivity, and which opposes the field to drive the electron for the movement along the direction of the field, and it leads to increase the resistivity. So hence if we increase the temperature, so for metal more number of electrons are there, more temperature leads to increase the random movement that will oppose the movement of the electron along the direction of the field, that is the external field, and it will increase the resistivity. So this is what the reason. Okay.
Yes, sir.
That's why for metal, the resistivity is the positive temperature coefficients of the resistivity. Because if you increase the temperature, resistivity will increase. Whereas for the semiconductor, the temperature coefficients for the resistivity is negative. If you increase temperature, its resistivity will decrease because the more number of free carriers will be generated for the case of semiconductor. Okay. Here another lines you can see here. This line from the center of the band gap. This line is known as the Fermi energy level. Fermi level. This Fermi energy level is basically another energy level which is defined as if which is defined as follows that if you consider at this energy level the probability of occupancy of an electron is 50%. Okay, what I told, let me tell you again and let me explain it what I wanted to mean here. Now, so far, I told you that in allowable energy states, the electron can occupy or the electron can reside. Okay. So, in the valence band, all the electrons, all the energy states are occupied by the electrons. Okay. In the conduction band, all the energy states are empty at absolute zero temperature, and some of the energy states are occupied by the electrons at finite temperature, and that depends on their how much energy states will be occupied by the electrons. That depends on the number of carriers available, temperature, and the energy band gap. Okay. Now, this is a statistical approach to define or to get how much electrons can reside or what is the probability of an electrons to reside in a particular energy states or the given energy states. Say, let me again explain here. Say up to this energy level, the electrons are completely occupied. Just here, if we consider, this is the valence band energy, EV. So below this EV, all the states are completely occupied. All the energy states are completely occupied. This is a valence band. Here, if you consider, there are very closely spaced energy lines are there, and all these would be occupied by the electrons. Now, if you consider the conduction band at a finite temperature, then from the valence band, some of the electrons jump to the conduction band. This is EC, and the energy states available in the conduction band that would be occupied by the electrons, right? Now the question is, for a given energy states, this, it is not known, it is a probabilistic matter, okay? Probabilistic that which energy states the one electron can occupy. At this energy, there are so many energy states are available. Also the electrons may jump into higher energy states also because there are so many free and empty energy states are there above EC. Okay, so is there any probability to occupy at these energy states? If it is allowable, allowable means there is some forbidden energy states or energy band. Forbidden means at which the electrons cannot occupy at all. Already we know that. And some of the energy bands which are allowed, that is at those energy band the electron can occupy, right? Now question is, for a given energy state, say for example here, this is say ET. ET is the energy states at a given temperature T, or say if we consider simply E1. Now what would be the probability to occupy and by an electron at this energy level. Are you getting my question? Are you getting my question? What I am trying to
Yes.
say?
Yes, sir.
Okay. Is it clear?
Yes, sir. Proceed.
Yes, sir.
Yes, sir.
Okay, so this is what just thing is the at this energy level, what is the probability to occupy by an electron? This energy state. Whether these energy states will be occupied by the electron or not. How we can get that? For a given temperature, because if you increase very much sensitive on temperature and dependent on temperature, if you increase temperature, there is a more probability to get more energy by an electron and jump into the higher energy states. Accordingly, if we increase the temperature, that also will increase the corresponding probability of occupancy of an electron, right? Just a minute. Just a minute. Okay. Hello. Are you?
Yes, sir.
Am I audible?
Yes, sir.
Yes, sir.
Yes.
Okay, my slide is visible.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. Bolo. Acha. Now, what I was talking that what we are discussing. Hmm. Okay, so this is what we are discussing that if we consider one energy states here, okay, say at this energy level, what would be the probability of occupancy of an electron? That means at this energy level, what is the probability at a given temperature to occupy by these energy states by an electron? So this can be obtained by Boltzmann distribution function, the Fermi-Dirac Boltzmann distribution function, and that is given by the probability of occupancy, that given by Fe, that is at a given energy level. Fe, this defines that the probability of the occupancy of an electron at a given energy state E at temperature T is given by 1 divided by 1 plus exponential E minus EF divided by KT. Okay?
Yes, sir.
So this EF is known as Fermi energy. Is defined as the Fermi energy. Okay. Now let us try to understand what is the significance of this distribution function and how it will change with the variation of temperature. Just let me another slide, empty slide. Okay. So this is what I started with. If E is equal to 1 divided by 1 plus exponential E minus EF divided by KT. Okay. Now, if we consider E greater than EF, or let us see first what will happen at E equal to EF. So, if you see here, this is what energy level, say E equal to EF. E equal to, for the case 1, the situation, E equal to EF. The energy E is equal to EF. Fe is equal to what would be Fe? You tell?
So 1 by 2.
1 by 2. So what does it indicate? Probability 1 by 2. What does it indicate? Yes?
There is 50% probability of
Yes. The chance of getting an electron at Fermi energy is 50%. Okay, and it is for at any temperature T, if you consider T greater than 0 only in that case. That means it does not depend on temperature. For any temperature, any finite temperature, the energy level at Fermi energy, the probability of occupancy of an electron is 50%. Am I right? Are
Yes,
you
sir.
getting this?
Yes,
Okay.
sir.
Now, if we consider, now next is 2. If at E equal to EF, okay, or for any energy less than EF, E less than EF and T less than T equal to 0. T equal to 0, what would happen? You tell me. If E is equal to 1 divided by E less than EF, then 1 plus 1 plus, you tell me what would be this value? E less than EF, exponential, then E, if E less than EF, E less than EF,
0.
then E minus EF would be
Zero.
give it is
Negative.
negative. E minus EF negative. So then it would be what? Exponential. I can write EF minus E divided by KT. T is 0 here. So this is what? That means I can write 1 divided by 1 plus exponential minus infinite, which is given by what?
Equal to 1.
What would be this value? It
So
would be
1.
1.
One.
1.
1.
it would be 1. So what does it indicate? Probability 1 means what?
That
All.
is
Yes. That
100%.
means it is confirmed. Probability maximum value is 1. That means what
Yes.
does it indicate? Look at this here. E less than EF. That means E less than up to E less than equal to, if I plot it along this is energy E, and say if I consider up to the energy EF, this is the energy EF. So at temperature T equal to 0, all the energy states, if I consider, if I plot it with the function of Fe, with the function of Fe, this along this is Fe, I am plotting it, and this value is maximum 1. So for T equal to 0, at T equal to 0, all these energy states below EF, this would be value, the probability value is 1. And this indicates that all the energy states below EF or less than equal to EF, all the energy states are completely filled by the electron at absolute 0 temperature. Are you getting my question? Are you getting it? Try to understand it. And accordingly, the Fermi energy is defined in another way. It is the maximum energy at which or up to which the electrons can reside at absolute 0 temperature. Is it clear to you?
Yes, sir.
It's clear. Let me explain it again. Look at this here. When E less than equal to EF at absolute 0 temperature, then this E minus EF becomes negative. Then the probability distribution function gives 1. This indicates that up to the Fermi energy at absolute 0 temperature, all the energy states are completely filled by the electrons. Okay? Is it clear?
Yes, sir.
Probability
Yes,
value
sir.
is 1 that indicates this. Now let us see the next case, case 3. If we consider E greater than EF, E greater than EF and T equal to 0, then you tell me what would be the value of Fe.
0.
0.
1 plus exponential
Infinity.
infinite. So this would be 0. What does it
0.
indicate? What does it
No
indicate?
chance.
Huh?
No
chance.
electrons.
No electron
elect-
is
No
filled.
electrons.
No electrons above the Fermi energy at absolute 0 temperature. Are you getting? That's why you are not getting any current or anything what insulator depending on that. At absolute 0 temperature, there the maximum energy is defined with the Fermi energy, and above this energy there is no electron. That's why above these energy states, no electron can reside. Okay, whereas for case 1, if already we have seen what we can see for T greater than 0, the probability distribution function Fe becomes half. That means if you consider this is the half, this is half, this is 0.5. Okay, so this variation at any finite temperature, say if we consider the distribution function will be like this, it would be symmetric about the Fermi energy. Now if we increase the temperature, the distribution function will be like this. Less temperature, less number of electron will have the energy greater than Fermi energy. And this is if we consider T1, this is if we consider T2, this is if we consider T3, then T3 greater than T2 greater than T1. And look at this here, at the Fermi energy, always it gives the probability half. Are you getting it?
Yes, sir.
Yes, sir.
Okay, good. So this is what the Fermi energy and the energy distribution function, which gives the probability of occupancy of an electron at a given energy states at a finite temperature, at a particular temperature. Okay. So if Fe is the probability of occupancy of an electron, this, then if I can take a prime E, then a prime E is given by, say, is equal to 1 minus Fe. What would be this? One minus Fe.
The probability that electron do not occupy.
Do not occupy. That means what? That means if I go to the previous slide, whenever the electron will jump to the conduction band, there will be gap would be created in the valence band. Here, one vacancy will be created, right? If the electrons jumps from conduction band, this is valence band, this is conduction band. So here, some vacant state will be created if it jumps from valence band to conduction band. These are called holes. These are called holes. This is what is called holes. Okay. Are you getting? Or if we consider this is the occupancy of an electron, then this defines the empty states. 1 minus Fe, if Fe defines the probability of occupancy of an electron at this level, then 1 minus Fe defines opposite of this, that is the probability of one vacant energy states. That means there is empty energy states, right? Then so the probability of empty energy states, or we'll say here as the holes, is given by 1 minus Fe, and if we simplify it, 1 minus 1 divided by 1 plus exponential E minus EF by KT, then what would be this value? Tell me. What would be this value? It is given by
Exponential.
so
Exponential.
1 plus exponent minus, so it is given by exponential E minus EF by KT divided by 1 plus exponential E minus EF by KT, right? Now, if we divide both numerator and denominator by this exponential factor, then what we'll get? we'll get simply 1 divided by 1 plus exponential minus E minus EF by KT. Can I write it?
Yes, sir.
Okay. So this you will remember that this is the if he defines the probability of occupancy of an electrons at a given energy states at a particular temperature, then 1 minus if he defines the probability of an empty state or the available empty energy states at which there is no electron at that energy level and at that particular temperature. Clear? Now let me come to the point of the Fermi energy here. So as per this, you can see here the Fermi energy state is available in between the just at the center of the forbidden gap. Can you see here? This is a Fermi energy states. This is Fermi energy states here. So for metal, it is within the allowable energy states. Whereas for insulator and semiconductor, it is decided at the center of the forbidden gap. Now already what we got that and we defined the Fermi energy level is the energy at which the probability of occupancy of an electron is half. And also, if we see already, I told you, and you know that this is a forbidden energy gap, so there cannot reside any electrons. So that means here there is some conflictness. What is that? How will we explain it? Are you getting my question?
Yes, sir.
Yes, sir.
Okay. So how you will explain it? What is actual things here? Yes, this is what the explanation is. There is no allowable energy states in the forbidden band gap, right? Now here Fermi energy is residing. This indicates that if there is any allowable energy states at the Fermi energy level, then if this Fermi energy state is allowable, if it is the one allowable energy states, then the probability of occupancy of an electron becomes half. But as there is no forbidden energy state, this energy state is not forbidden allowable energy state, or it is a forbidden zone. So there is actually no electron. There cannot reside any electron. Thing is this: if such energy state exists or it is allowable, then at this Fermi energy level, the probability of occupancy would become half, or the 50% of those allowable energy states would be occupied by the electron. Are you getting it? Just like for the case of metal. As you can see, for the metal, it is within the allowable energy states, and this defines that all these allowable energy states at this Fermi energy level is 50% is filled by the electron. Okay, and whereas it is not allowable, so there is no electron. But if it is allowable, then the 50% of the energy states will be occupied by the electron. Right. So this is what the Fermi energy distribution and the probability concept of occupying an electron at a given energy states at a particular temperature. Now there are different types of semiconductors so far. What I told you, the semiconductor material that provide the electrical characteristics between the metal and semiconductor, and also the band gap is in between the metal and semiconductor. Right. So now there are two types of semiconductor. That is, one is intrinsic semiconductor material and extrinsic material. Intrinsic and extrinsic material. What does it mean? So intrinsic semiconductor or intrinsic material means there is no material, but the lattice defects. There is no defects in the lattice also. Okay. So no impurity means what? Actually, if we consider a silicon or germanium materials, then those materials consist of only with silicon atom or germanium atom. There is no other impure or any other atoms will exist in those materials for this intrinsic material. Okay, that is pure in all aspects. And extrinsic semiconductor is what? Extrinsic semiconductor which consists of, in addition to the intrinsic material properties or intrinsic material atom, it will consist of some others atoms. Okay, the material contains some other atom. Okay, then whenever it will be formed like this, then it is extrinsic semiconductor. And this process of adding some other type of materials into the intrinsic material is known as doping. What I told, the process of adding some other material to the intrinsic material is known as doping. And depending on the types of materials we are uh, doping into the intrinsic material, it provides different electrical carriers, charge carriers to conduct the currents, and based on that, we know that it is N-type doping, N-type semiconductor and P-type semiconductor, right? So what is this N-type semiconductor, P-type semiconductor? How we can get it? How we can get it? Do you know it? Huh?
Yes.
Doping, you know, na?
Yes, sir. Yes, sir.
So that's why I'm going faster here. This already I explained. That's why I'm skipping it. So, and this is one important features in semiconductor, that is the doping. And what is this important features, that let us see. So now if you consider, this is what the atomic structure of the semiconductor. This, if you consider one silicon or germanium, it gives this type of semiconductor crystal structure. Do you know? Do you have any idea about the crystal structure of the solid or materials? Do you have any
Yes.
idea?
Hmm.
And how the what is the atomic configuration? Yes, Bolo. What is the atomic configuration of the silicon or germanium? How this they form the covalent, how they are bonding with each other? How many valence electrons are there for silicon?
4.
4 electrons. And you know that there must be 8, or it should be formed with inert gas like atomic structure configuration to make it stable, right?
Yes, sir.
Yes,
So
sir.
so this 4 valence electron is formed 4 covalent bonds with its 4 nearby atom, and that's why it, as a result, the total 8 electrons is always associated with one atom, and that form the in the atomic structure, it forms a covalent bond, and that's why there is no free electron in semiconductor like silicon as well as in germanium. Okay. What is the atomic number of silicon?
14.
14. Good.
14.
And germanium?
30.
32. Okay. So both of its for both of these, the outer valence electrons is 4, and that forms a covalent bond. And if we see here, the uh, for intrinsic silicon or germanium, as there is no free electron, so it provides the conductivity or the currents only due to the generation of the carriers due to temperature. That is thermal generation of the carriers at finite temperature, or due to the application of external force. If any covalent bond is breaking, just if it breaks, then the electron and hole pair will be created. This electron, suppose it is break, this covalent bond is break, then this electron will be now coming here and it will move randomly, and it can decide to any other atom also, and then another a vacant state will be created here. So this is what is known as the generation of electron hole pair. So this vacant state is whenever the due to breakage of uh, one covalent bond, an empty state is or vacant state is created. This vacant state is known as hole. Okay, and this is known as this process of, or the due to breaking of this covalent bonding, the electron hole pair is generated. So now if more breaking of covalent bond is there, more electron hole pair will be generated. That's why if you increase temperature, the atomic vibration will increase, and that leads to the break the covalent bonding, and that will increase the generation of electron hole pair and will increase the conductivity. But this for intrinsic semiconductor, the amount of conductivity or the current what we are getting, that is not so significant. Okay. So that's why how we can increase the conductivity of the semiconductor. Also, that is what would be its conductivity, that is controlled by the user as per the requirement. And this is basically one great advantage of semiconductor that we'll see. Now, if we add another types of material of periodic table 5, say for example, arsenic, antimony, phosphorus. There are 5 outer 5 valence electrons are there. So now these 5 valence electrons will actually this 5 valence electron actually will give first out of these 5 valence electron, 4 will form a covalent bond, and another electrons that is not associated or attached with the covalent bond. It is just bounded with the phosphorus atom or whatever the arsenic atom. Just look at this. It is with the bounded with the Coulombic force. If you consider one atom, what you know, in the nucleus is there at the center with the positive charge, and at the outer orbit the electrons are revolving. So the 4 already, 5 out of the 5 electrons, 4 already formed covalent bond. This 5th one cannot make any covalent bonding. So that's why it is attached only with the Coulombic force. With the Coulombic force, what? This is due to this positive nuclear charge and with the electronic force. Are you getting it?
Yes, sir.
Yes.
Okay. So now
We
this
have class from 11 a.m.
Sir,
just
Sir,
one
we have a
minute.
class from 11.
1 minute, just 1 minute. Let me just this one second. Now, if we look at this here, as these are attached with the covalent bond like this, and this one is attached with the nuclear force, only the Coulombic force. So what happens? This you can get electron hole pair only when the covalent bond is breaking. Also here there is a scope that If this, anyhow, this electron is breaking, and this Coulombic force is very less as compared to this covalent bonding force. That's why with small energy, small external energy, this covalent bonding force, this Coulombic force is we can break, and now this electron emits from this atom. Okay, and whenever it emits, effectively it becomes positively ionized, and now it provides the free carriers. In this way, as many number of atoms you will add, it will provide the more number of electrons. Just like this, if you consider the number of donor atoms is in D0, then it will provide the 90 plus that ionized atoms will be there, as well as free electrons will be generated. And this N will create the concentration of free electrons that will create. And look at this, as the number of electrons will increase the conductivity, so more doping, more electron concentration and the conductivity as well. Okay, so then in the next class, just we'll explain then what is the role of holes in providing the current that you think. In the next class we'll discuss. Okay, what would be the effect of holes if you apply the force, or in due to the breakage of the electron hole pair generation. We are discussing only about the current due to electrons, but how the holes will contribute the total current, that you think about it, and we will discuss in the next class. Okay, all of you got the question?
Yes.
Yes, sir.
Okay. Okay, sir. Okay, thank you all. And Antara and all others, just you inform me if you have any other free slot available in the next week. Okay. I need some extra class. Okay.
Yes, sir. So I have mailed you about today's extra class from 12 a.m. 12 p.m.
From 12 p.m. today.
Yes, sir.
अच्छा ठीक है. Okay, okay. From 12 to 1 p.m.
Yes,
Right?
sir.
Okay,
Yes, sir.
ठीक है, ठीक है.
Thank you.
Thank you. You may leave now.
Thank you, sir.
Yes.
Thank you.
Thank you all.
Thank you, sir.